Hello, everyone, and welcome to another live session for the MOOCs. And the floor is open for your questions on any topic.
Okay, the first question is, what type of elasticity, if any, can be found in the universe?
Interesting word, elasticity. So I'm not quite sure what you mean by that, but let me just take that it might allude to the properties of space-time. So the universe, as we understand it, is a sort of large space-time container. It's expanding. It's been expanding for 13.8 billion years. And the elasticity that the universe has is based on the expansion of space-time. That's an interesting phenomenon because the cosmic expansion is reference to general relativity. And general relativity is a mathematical theory of gravity, where space-time is a manifold. A manifold is a term in pure mathematics. Obviously, space doesn't have to have anything in it. It's a pure construct of the mathematics of general relativity. And in that sense, it's infinitely elastic because space-time in general relativity can be bent in any shape whatsoever by the mass energy it contains. So curvature is part of the framework. Expansion or contraction is part of the framework. And general relativity actually puts no limit on the suppleness of space-time. So in terms of elasticity, space-time can expand at any rate that it wants. This leads to interesting situations such as the universe early on having any 2 points move away from each other faster than the speed of light. There's no constraint as in special relativity where the speed of light is an absolute limit. Space-time can expand much faster than light speed and did so for the first few billion years after the Big Bang.
All right, the next question is also from someone who is on with us live, and they ask, how many pounds of ozone-destroying material is created from a rocket launch, a NASA rocket launch?
Interesting. Well, I don't know. It depends on the rocket, of course. A typical, it really does depend on the rocket because there are very large differences in number of pounds. If we talk about the Ares rocket, the new launch capability that NASA is developing, it is indeed true that the kinds of rocket fuel being used have their waste products. I mean, we're talking about a chemical combustion process involving a sort of highly volatile kerosene compound and liquid oxygen. And indeed, there is some level of ozone destruction connoted by that kind of a combustive process. So we're talking about tens to hundreds of tons of this fuel per rocket launch. The truth is that's sort of a drop in the bucket, and so individual rocket launches at the rate they're going to happen in the foreseeable future simply do not have an effect on the ozone layer. A far bigger problem, of course, in the 70s and 80s was when the refrigerant that's used in household refrigerators, the chlorofluorocarbons, were escaping into the atmosphere, and the ozone layer was been depleted at an alarming rate during the 70s and 80s. But by international agreement, one of the interesting success stories in heading off problems with our climate and atmosphere, changes to the regulatory environment of those compounds really mean that that ozone depletion and the huge holes that would appear annually have shrunk substantially. So we can head that off, and I think the space program is really a limited liability on the atmosphere.
All right, another question comes from email, and they ask, do you think dark matter is a good source of energy for the world?
It depends a lot on what dark matter is. The current best candidate is an extension of the standard model of particle physics called supersymmetry, which involves the unification of 3 of the 4 forces of nature, excluding gravity. Out of those unification theories, which essentially posit shadow particles, fermions and the bosons, that is the integer and half-spin particles, each have shadow particles in supersymmetry. And the lightest stable massive particle predicted out of supersymmetry has the properties and the abundance to be a candidate for dark matter. And there are various names for these particles. Neutralino is one of them. So if that's the dark matter in the universe, it's a tiny subatomic particle with very weak or absent electromagnetic interactions, but it's a massive subatomic particle, then it doesn't have any obvious benefit for us in energy terms. And that's partly because of the properties that make it dark matter. The handle we can get on particles to turn them, to liberate them for energy, apart from just turning their mass into energy, which is extremely hard to do outside of an annihilation process, is when they do have electromagnetic interactions or are charged. So these are neutral particles that have no electromagnetic interactions, and that actually completely limits your ability to involve them in interactions or exchanges that might liberate energy. So almost certainly the dark matter is not going to be useful for energy purposes.
The next question is from Ed via email, and the question is, can you give me the basic technical requirements for detecting the cosmic microwave background radiation here at ground level?
So the microwave background radiation it's really dictated by the temperature. So it's a black body, which means it has a thermal spectrum, which is because it was in equilibrium, was an equilibrium process early in the universe. And it has a temperature of about 2.73 Kelvin, which means the peak wavelength of the radiation is somewhere around centimeter wavelengths. So if you want to detect the microwaves of the Big Bang, then you can detect them over a broad frequency range from tens of centimeters down to millimeter or less than a millimeter. But the sweet spot for detection and the largest energy density, if you like, is around the centimeter, few centimeter range. So you would want a radio telescope, a radio dish, and a receiver that's detecting centimeter wavelengths. This is not the kind of stuff that amateur astronomers necessarily do that easily, because those are fairly sophisticated detectors. They tend to have to be cooled, and they're hard to find for any amateur purposes. But so I'm not. If the question is this something an amateur can do, or you can get on the ground floor of, then that's pretty difficult. Every now and then, this equipment is surplused, however. Also, the signals are very uniform. They have almost no variation across the sky. So what you're actually trying to do is a very accurate differential measurement of radio signal. So that means typically you want a wide beam, so you want a large angle beam of your radio telescope, not a fine beam because you're not looking at point sources. And you want to be able to oscillate between the sky and a standard load that represents a low temperature in radio astronomy terms, because it's a differential measurement of an excess of this very cold temperature radiation. So it's called a differential radiometer. That's the technical name for the radio equipment that's used. And that's fairly specialized equipment. And that is definitely not the kind of thing you can build easily yourself or buy off the shelf. It's very different from the average sort of shortwave or ham radio equipment. It's very different from even conventional classical radio astronomy.
All right, the next question is from email, and the person asks, has anyone figured out yet why time does not move backwards? And is there any good reading or research about this topic?
To answer the second part first, yes, there's a lot of literature on the physics of time and the philosophy of time even. It's an active field of philosophy too. I off the top of my head, I can't recommend books or articles, but there are entire books and conferences on the nature of time from a physical standpoint. So it is and remains a mystery of modern physics, because there's a dichotomy, there's a conflict, if you like, between two things, between the almost perfectly reversible nature of subatomic and microscopic processes. If you take almost all subatomic interactions, and then which have an equation and there's a time arrow where the reaction goes in one way, you can watch that reaction occur or make it occur in the opposite direction. In other words, time reversible. There's a very slight exception to this in particle physics world, where there's a very slight violation of time, pure time symmetry in a certain class of subatomic interactions. But at the 99.999% level for all the interactions we see in microscopic physics, they're time reversible completely. There's no sense of time forward or backward. So that's the reality of the microscopic world. The reality of the macroscopic world of large objects, including the universe, including the Earth itself, is that the second law of thermodynamics dictates a steady increase in entropy over time, and it's that which gives the arrow to time. So the speculation is, and it's just a speculation, it's not a true explanation for these things, that one of the reasons we may experience an arrow of time is that the entropy of the universe as a whole, including the objects within it, is, or actually started quite low, so low amounts of disorder, moving towards higher amounts of disorder. If the entropy of the universe in the initial phases had been much higher, then perhaps the time arrow would not be as obvious. So that essentially puts it down to initial conditions. The way of thinking about this is that the entropy in the universe we live in at the moment, there are about 10 to the power 80 particles, mostly dark matter particles, and 10 to the 88 photons, that is 100 million photons for every particle. And photons, since they're disordered energy, they represent the entropy of the universe. So this large number of photons per particle indicates a universe with fairly high entropy. As the universe evolves, its eventual end state will consist of disordered radiation, the microwave background itself, and then collapsed objects like black holes and neutron stars. Black holes embody 100 million times the entropy of a star that's the mass of a black hole. So everything that goes into a black hole is sending it into an even higher entropy state. So as the universe fills with black holes and diffuse radiation, its entropy will increase. Now, if you look at inflation, which is the model for how the universe started and went through an exponential expansion early on, then most inflationary models posit a very low amount of entropy. That's just part of the conditions that set up the inflationary process. So the standard Big Bang does have a progression from fairly low entropy at the beginning in the initial conditions of inflation to large entropy now. And in that context, then we would expect an arrow of time. If the initial conditions had been different, if the early situation had been more chaotic, if there had been, say, large numbers of black holes, small, tiny black holes in the early universe, the entropy would have been a lot higher, and we might not have had a universe where time had a forward arrow.
Right, the next question is from Sana, who asks, what can we do what can we do to at least prevent global warming for now?
Well, that's sort of be venturing a little beyond astronomy and sort of my core expertise, but the big answer to that question, the approximate answers to that question, of course, are extremely difficult because it's become a political question as much and an economic one as much as a scientific one. You know, the ultimate answer to that question is that we need to move to what we would call a hydrogen economy. So we, at the moment, live in a carbon economy. So we're obviously depleting non-renewable resources like fossil fuels, oil, gas, coal, and still gaining the majority of the world's energy from those sources. The renewable fraction of the world's energy is a small fraction. I think it's around 10%. And that's like wind and hydroelectric and solar. And the economics of those forms of power are not yet viable. So we have to make those forms more economical. But of course, the ultimate goal is the cheapest and most efficient form of energy possible. And they're liberating the energy from a combination of hydrogen and oxygen non-explosively to form water, which is something that a fuel cell does. Hydrogen fuel cells are probably the ultimate goal of an energy economy because they have no waste product that's damaging to the environment. They don't actually liberate much heat either. Their energy liberation is fairly efficient, and they use completely abundant resources as their raw ingredients rather than digging things out of the ground. So pending a move to the hydrogen economy, which would be an ultimate answer to the climate change issue, then we sort of have to incentivize the renewables and probably on the converse side penalize the non-renewables, or at least use carbon credits so the dirty producers can swap energy and credits with the clean producers. And we could probably muddle through if we do that.
All right, the next question is from Chaitanya Vasista via email. Which among string theory and loop quantum gravity is a better candidate for a theory of quantum gravity?
There is such a spectrum at this point of theories, the ones alluded to in the question. String theory, of course, is not one theory, and loop quantum gravity is a variant of one of the quantum gravity spectrum of theories. Just to take string theory for a minute, it was sort of realized after the initial string theory work in the 1980s. It was realized in the 1990s that many of the sort of formalisms of string theory that people were working on were fundamentally related, and so this concept of M theory came out, where there was this larger landscape, a sort of super landscape of string theories of which people were working on little pieces, trying to work through the mathematics of the formalism. Because the hard thing in string theory is actually doing the calculations, actually getting to a meaningful point. The goal of string theory initially is simply to reproduce standard physics, the standard model of particle physics. String theory posits, tiny entities that are, trillions of trillions of trillions of times smaller than atoms, and they're operating at equivalently large energy scales as their small space scales. And these are completely inaccessible from experiment right now, and possibly forever. So string theory is also a multidimensional theory involving, depending on your variant of the string theory, anything from 6 to 10 or 11 dimensions of space-time. And each of these formalisms has to be developed separately and worked through. And it presents its own mathematical challenges. So it's extremely difficult theory to work in. And you're also in some alien landscape because you're working in this multidimensional theory that has no reference really to everyday lab phenomena. And so your goal is to work through enough of the formalism of the theory to approach predictions of what happens in the world that we can actually measure. And that, of course, doesn't prove that your string theory is the ultimate theory of nature. It just proves that it's at least a viable theory because it reproduces the physics we know. And it's probably fair to say that much of the last 15 or 20 years' work on string theory has been involved in developing a small fraction of the possible variants of string theory and working them through or developing them sufficiently to be able to reproduce conventional known physics. That itself has been so hard that it's taken over a decade. So the progress in string theory has been slow, obviously not because the people doing it aren't up to the job. They're some of the smartest people on the planet. But because the theory itself, the math, the formalism has to be developed from scratch, and it's extremely difficult. And that's, as many people have noted, has led to a bit of a backlash in the physics community against string theory for having consumed the talents of so many young physicists with not really that much payoff so far. So, to summarize the answer to the question, there is no current candidate among the various related string theories or variants of string theory that is looking like it's the answer. And that's partly because the string theories are still not fully enough developed to judge them. The thing, of course, that we really want is for these variants of string theory to make unique and testable predictions that allow us to discriminate between one variant of string theory and the other, which is how we test all theories. And string theory is not mature enough to do that right now. So it's not that the field is stuck. There's clearly hundreds of people around the world working on it, but the progress is kind of frustratingly slow. And some people, it has to be said, are losing faith, if you like, maybe an inappropriate word, but they're losing faith that it is the way forward, that the fundamental nature of matter will be described in the end by string theory and not by something else.
The next question is from Daniel Williams via email. Recently, in humanity's pursuit to other star systems, a theory called the Alcubierre Warp field has been created, proposing to warp space-time through expansions and contractions to move a ship large distances quickly without surpassing light speed. Do you think this is a viable option to take humanity to other solar systems? If not, what is?
So that, I've only read one of the various papers about that idea. It attracted some attention. It got a little boost because NASA, one of the NASA centers, their engineering area, took it seriously enough to sort of have a conference where the idea was discussed, and invite the designer of the theory to visit and talk. And so it's got some credibility, but it also has had some physicists say that this is simply, this is inappropriate physics, or it's physics that can't happen, or especially it's a technology that can't happen, that space-time cannot actually be manipulated in this way so as to produce propulsion. And I simply am not expert enough on relativity to judge those arguments. But I would say the concept is still controversial in those terms, and probably a majority of the physicists I've seen reacting to it are deeply skeptical, both of the underlying physics at some level, and certainly of the fact that it's projecting into a technology that could be realizable. So in the absence of that mechanism, what are the mechanisms? Well, they're just more standard type of mechanisms. NASA resuscitated a couple of years ago what it called the 100-year Starship project. So NASA sort of put on a long hold their conferences they used to hold every few years about developing new technologies to go to the stars. Not faster than light travel, not warp speed, not something that's Star Trek-like, but sort of substantial fractions of light speed, 10, 20%, which do bring the stars within reach in a generation or so. So NASA's now actively working on those ideas again, and they involve, electromagnetic pulses. They involve obviously fusion-driven machines. They also involve capture of the fuel as you travel through the thin interstellar medium, because that's a lot cheaper and easier than having to bring the fuel with you. Solar sails are a very old idea, 50 or 60 years old, and they're back on the table and being actively investigated. So NASA is looking at probably 6 or 7 technologies that are not based on radical physics. They're based on conventional physics, and they're just working the engineering of these ideas now to try and see if they can be, a test bed can be produced. And some of them are very primitive. I mean, the simplest idea of the fusion propulsion system involves creating, thousands of small nuclear fission, not fusion, but fission explosions, like a dirty atomic bomb, behind a reaction plate of a spacecraft. And so just by Newton's law, propelling it to a substantial speed. That's a pretty primitive mechanism, actually. But those are the kind of mechanisms that we could probably do the engineering of with no new inventions.
Next question's from Mike C. via YouTube. So what have we learned so far from the Juno project now that we are in orbit?
Most of Juno's results have not yet been announced, and Juno is really in its very early phases. One of the main goals of Juno, of course, is to diagnose the interior properties of the giant planet, and in particular to try and diagnose the interior mass of the rocky core. There's very little hard evidence from previous missions, flybys, of what the mass of the super Earth sort of rocky-sized object that we believe is at the center of all the gas giant planets. Previous estimates in Jupiter have ranged from a couple of Earth masses up to 5, 10, even 20 Earth masses. And those differences are quite significant. They make a big difference for how Jupiter formed, and by extension, how giant planets and other solar systems form. So that's probably the most important thing, single thing that the Juno mission will determine. It will determine the mass of the rocky core of the planet. And it will also show the interior structure of the atmosphere in better detail. It's still surprisingly hard to model the atmospheres of the gas giant planets because the depths are so large. The stratification and the differential velocities are large. These are not things you can model, in a lab or in a wind chamber or some analog system using liquid. So Juno is going to do this. It's also going to produce a much more detailed map of the Jupiter-Jovian magnetic field and sort of give a sense how that originated. And how it originated, of course, is connected to the rocky core because the magnetic field would be tethered in that rocky core. If you only have a gaseous object like the sun, the magnetic field is untethered, and so will typically, in a differentially rotating object, the magnetic field will scramble, reverse, and so you'll have things like a solar cycle, which doesn't happen with a planet. So basically, it's still too early days for Juno, and the mission people are being fairly cautious about eking out results ahead of a full analysis.
The next question's from Callisto via email. It seems difficult not to think that sun activity is directly linked to our climate and its changes. What role does the sun play in our climate, and do you think we are heading to a little ice age in the next 10 or 20 years?
So there are unquestionably solar effects on climate, and we know that. So there are correlations with the solar cycle, the 11 and 22-year solar cycle, with subtle climate variations. There's, of course, the famous, since you're alluding to the ice age, there's a famous longer-term correlation of sunspot activity with climate, where in the Maunder minimum, so sunspots, of course, have been tracked since the invention of the telescope, that's 400 years. And in the late in the first century after the invention of the telescope, the sun went through an extended sunspot minimum for multiple cycles when sunspots essentially disappeared for some period of time, a couple of decades, and that corresponded to the mini ice age, especially in the northern hemisphere in Europe, when down into the middle European latitudes, lakes and canals and small bodies of water were frozen even into the summertime. So that's the basis in the few hundred-year history where we have sunspot records of how climate and solar activity, the solar cycle, are connected. There are other connections, of course, which relate to the high energy emissions from the sun. So, you know, the reason to believe that the sun doesn't totally drive monotonic climate change, that is the global warming that we're seeing, are that if you look at how the sun's energy varies over a year or from year to year, the variation is very, very small. Even the sunspot cycle only varies the sun's output by about 0.1%. And so the sun's total energy output year to year in the visible part of the spectrum is of order or less than 100, 1 part in 1,000. And that's simply not enough to cause the Earth to warm or the climate to vary dramatically from year to year. However, if you go to the larger energies, the high energy spectrum, short wavelengths, UV and X-rays, the tail of the dog, if you like, is wagging pretty fast and is quite significant. And so the yearly, depending on the nature of storms, prominences, superstorms on the sun, and which can be episodic and quite dramatic, the far UV and soft X-ray output of the sun can vary by literally dozens of times larger than the visible light. So we're talking now several percent up to 5 or 10% in extreme cases, and in the historical record it seems like it can be that high, maybe even more. And those would undoubtedly have climate effects, temporary and perhaps long-term. As for the entering a new ice age, that is completely unclear because solar modeling does not, of course, predict what the sun's going to do, the Maunder minimum. If something like the Maunder minimum was heading our way, there's no way stellar modeling or the very detailed information we have from satellites would actually predict that, be able to predict that. We don't know what the triggering event for these longer term changes in the sun are, which is why NASA is actually putting quite a lot of energy into this topic. Obviously, the sun, the NASA and the Europeans have had sun satellites, starting with the SOHO mission, which went for 15 or 18 years, and then its successors, which are much more precise missions. So we've been monitoring the sun really close and looking then with Earth-looking missions from NASA at the effects of the sun on the Earth in the last decade, and that's just a very big research subject. But the simple answer is we have very little predictive power.
The next question is from Robert Harold via email. A great deal has been made about exoplanets. Many of the discoveries have been gas giants and planets with a close proximity to their stars that suffer from high temperatures, that have little, if any, atmosphere and strong tidal stresses. We are, I thought, looking for life. Why get excited about environments that, in all likelihood, cannot sustain life when we have our own gas giants?
So the goal of exoplanet research, at the heart of it, is to understand the architecture of solar systems. We want to know whether our solar system is typical. We want to know what the incidence of worlds around other stars are. And yes, the big hook in that is finding Earth-like worlds or habitable planets. But to do the research, you have to find the whole population. And so, while we can look at many of the discoveries of these hot Jupiters or gas giant planets on close-in orbits and just say they're not really that exciting or interesting to find more of them or to have lots of them because they're completely uninhabitable. They're tidally locked, for instance, around their star, so there are huge, extreme temperature variations with the sun face essentially being blasted and ablated by the star that it orbits. So yes, these are not interesting planets, a lot of them, or most of them, in fact, for the search for life. But we don't know what all the habitable situations among exoplanets are. It can be possible, for example, when you're looking around dwarf stars, as we now are for planets, to find habitable planets that are quite tucked in, quite close to the star. And even the tidal locking issue doesn't necessarily guarantee the planet will be uninhabitable. Of course, you could have a terminator, like in the principal Mercury has a terminator region where it's room temperature, even though the far side is impossibly cold and the near side is impossibly hot. So you could have a tidally locked planet that has a habitable strip, if you like, around it. Or you could have large enough circulation patterns in the atmosphere of the planet that's close to a star and tidally locked so that it regularizes or equalizes the temperature and into a habitable space. And so we're only just beginning to learn about the atmospheres of these planets and how they circulate and how well they equalize temperature. So it's a little too early to be totally sure what's going to be habitable and what's not. So we need to start by looking in all the possible environments. And then ideally, obviously, we want to say per system or on average, in what fraction of the cases do you find terrestrial planets in habitable orbits for around all stars, not just sun-like stars. And I would say the statistics to make that determination are, Kepler has helped enormously, but there are other surveys that need to be done, and we're probably 5 years away from knowing that. And that will answer the question of what the incidence of habitable planets is and tell us, their incidence relative to the oddballs, the hot Jupiters, the things that we might not be as interested in for life.
The next question is from Cecil in the live chat. What is causing a large number of galaxies to move toward a particular part of the universe? What impact, if any, will this have on the whole of the universe?
So the issue of bulk galaxy flows, the term describing this phenomenon has varied over the years, and I'm pretty sure that's what the question is alluding to. So the overall situation is cosmic expansion, universal expansion, every galaxy moving away from every other galaxy. Hubble flow is the term for that, of course. But that's simplistic, and space-time may indeed be expanding uniformly in a Hubble flow sense. But galaxies, of course, tend to cluster. They have gravity, and that gravity sort of exempts them from Hubble flow and means that they can aggregate to form clusters and even superclusters. And as people start to look at larger structures in the universe, they've found some interesting structures where thousands of galaxies or even tens of thousands of galaxies over a region that's hundreds of millions of light years across all appear to be loosely bound together, not tightly bound like a rich cluster, but moving towards each other, and so exempting themselves from the overall cosmic expansion. And that's sort of the phenomena alluded to in the question. And these situations are pretty interesting because they're interesting fundamentally because if we find a really big set of galaxies that are all moving towards a common point and not partaking in the general expansion, if at some point it becomes a violation of the fundamental assumption in cosmology, which is called the cosmological principle, that the universe is homogeneous and isotropic. So that assumption, which is central to cosmology, all the cosmological derivations done by Friedman and others early in the last century involve the assumption of isotropy and homogeneity, is that the universe is the same in every direction, that's isotropy, and the universe is more or less, on average, the same in every location, that's homogeneity. And what does that mean? It's obviously not true in detail at the level of a single galaxy or a cluster of galaxies, but it means on scales that are perhaps 5% of the 3 to 5% of the visible universe diameter, you should start to see things being smooth or uniform wherever you look. And that's why structures or situations where tens of thousands of galaxies are all moving towards a common point, exempt from this expansion, are starting to be tricky, because those are scales of more than a few percent of the horizon size or the visible universe size. And so it's not predicted in cosmology that you should have such a large structure forming when the universe is supposed to be smooth at all locations. At the moment, nobody is claiming that these situations, the handful that have been found, violate the cosmological model, and we have to go back to square one. But they are several of these situations are at the point where they're kind of a pressure point against the standard cosmology and the standard Big Bang model, and creating some discomfort amongst cosmologists because it's not predicted.
Our next question is from email. Just seriously wondering if it would work to somehow launch our literal mountains of garbage into a black hole or the sun. Would that eliminate our waste issue? And if it was feasible, would it be ethical? What might be the long-term consequences?
So using I'd say, it's a good question, and I'll take it from being not sinking our garbage or detritus or things we want to get rid of into a black hole, because we don't have a black hole. The nearest black hole is 40 or 50 light years away, I think, maybe 100, very far. So, but the sun is a reasonable place where you could, send things, gravity pulling inward, so it's not too energetically expensive to send things towards the sun and into the sun. Is that a reasonable place to send our garbage? And the answer simply is no, because the energy costs of, it's part of the private space program now that what Elon Musk and Richard Branson and Jeff Bezos are trying to do is lower the cost per kilo or per pound into low Earth orbit by an order of magnitude. And even if you get that cost down to like $1,000 per kilo or something like that, which is what you would need to do to have a booming private space industry, the cost of the sheer thousands, millions of tons, the amount of garbage generated per person on the planet is literally millions of tons a year. I don't remember how many hundreds of millions, I can't do the math in my head, but it's just such a phenomenal amount that the launch cost of that is tens to hundreds of times world GDP. So the simple answer is no, you couldn't possibly get that stuff into orbit, let alone, could you then get it into the sun and destroy it? Now, where the question becomes a little more interesting is when it comes to, say, nuclear waste. So things that are considered so toxic or so difficult to dispose of that it's possibly worth the energy cost to get rid of them in space. And really, you just need to get rid of them in deep space, because space is empty. You don't need to entomb them in the sun or in a black hole or any more exotic location than that. You just need to get them out into Earth orbit and then off into deep space in canisters or contained somehow. Or maybe you don't even care. If they disperse, it doesn't matter if there's no life form there. And even at the level of nuclear waste, you're still talking about tens to 100,000 tons a year. The world generates a lot of nuclear waste, dirty waste, that is, from fission reactors. And people have looked at the economics of that, actually, and it just is so much cheaper to find a place underground to bury it or in a deep sea location. And as we know, the issues there are nobody wants it in their backyard if it's in a mine or under a mountain. And in the deep sea, the issue is that it's more expensive to put it there, and the undersea world is not totally geologically stable. So how can you ensure that those deep buried canisters will not eventually rupture and then leach into the seawater? Disposal of even the most toxic things we have to dispose of is still better done on Earth, but even then it's problematic.
The next question comes from Ram via email. I would like to know if quark stars exist, and if so, are there different types of quark stars? In addition, in a black hole within the event horizon, does matter exist as only quarks?
So the concept of a quark star has been around, actually for decades now. So it's a concept that is theoretically viable, because that theory was developed in the 1970s, I think, was the first time papers were being written about quark stars. So in extremely the principle here is that is in extremely dense states of matter approaching the matter of nuclear material, so neutron star, black hole type densities, you can have situations where quarks are liberated. As we know in normal nuclear matter, quarks are contained by the strong force, which is like a very strong elastic that prevents the quarks from appearing freely. But at sufficiently high densities, the quarks, if not completely liberated from the star itself, they can freely move around within the nuclear matter of the overall star. And so that becomes a quark star, where the quarks are interacting with each other and more free, more liberated to move through the medium, much like electrons are more liberated to move around in a conductor than in an insulator. And you get some interesting behaviors when quarks can do that. So have we got any evidence that quark stars exist? No. It's very difficult to have evidence that quark stars exist because the behavior of quark matter in the aggregate, looking at a lot of it, a star core's mass of it, it's not really going to be any different from normal matter. It's not going to manifest any electric charge or electrical behavior. Gravity is obviously just going to be the same as the sum of all those particles. So you would have to be able to inspect the surfaces of these stars in detail to get a hint that the quark matter was there and that it was showing some behavior. Just like with neutron stars are very interesting things that happen, star quakes and very interesting nuclear phenomena on the crust of a neutron star, but we've never been able to inspect a neutron star at that level too. So those are just pure theoretical arguments. So quark stars remain hypothetical. The physics they're based on is fairly well established physics, so I think most theorists don't doubt that they could exist or the quark material could exist and have interesting properties. But nobody that I've seen has shown a way where we could actually diagnose that kind of matter in the nearby universe.
The next question is from Jerry Murphy via email. In the movie Gravity, the story centers on a Russian satellite that's been destroyed. Its debris circles the Earth in the same orbit as the ISS. The debris causes significant initial damage and every 90 minutes circles around to do more. Question is, if the shuttle and the debris are at the same orbital distance, would not the shuttle be moving at the same rate of speed and therefore never encounter debris, so that the debris would be following the shuttle or the shuttle following the debris, depending on how you look at it?
Yes, if the debris were originating in the same location as the shuttle, I mean, just imagine that something was destroyed near the shuttle in its existing orbit, then that debris would get some velocity and some initial velocity from the explosion itself, but would generally be following, in its high speed of orbit, would generally be following the same orbital trajectory as the shuttle. So the premise in the movie and the premise in general of the danger of space debris is that the originating objects for the space debris are in all sorts of different orbits with different trajectories, essentially, even though they're roughly the same altitude from the Earth and they're orbiting at roughly the same speed, the orbital speed that all objects would orbit at to take an orbit in 90 minutes. So it's the relative velocity, like in a vector, between two different orientations of the orbit that creates an extreme danger. Obviously, if they're in a counter-rotating to each other, just because of the nature of the original objects, then they have, the impact speed is twice the orbital velocity, which is a fantastic amount of kinetic energy, and something that's a BB-sized pellet would completely rip through the hull of any spacecraft that we have. So with the typical difference in the trajectories of the debris at that altitude, the net velocities or the impact velocities are thousands of miles an hour, up to tens of thousands of miles an hour, and that's a catastrophic velocity. So space debris is extremely hazardous in most cases.
The next question is from Steve Kofsky via email. Please explain how, if at all, quantum physics is relevant in cosmological research efforts.
Well, I think the biggest way that the quantum physics has become relevant to cosmology now is because of gravity waves. I mean, basically, now that gravity wave detection is happening routinely, we have 2 confirmed detections and 1 tentative detection from that first LIGO run, and we have the expectation of a new gravity wave event every few weeks or every month for the foreseeable future, it's sort of like game on, because gravity waves are a quantum scale phenomenon, and yet the sensitivity of LIGO is such that we can see gravity waves substantial distances across the universe. The first two events, 1.1 and 1.4 billion light years away. And some of the larger possible events, I mean, the first event was a very large black hole pair, but gravity waves of even larger black holes, maybe a small black hole or a small object falling into a big black hole in the center of a galaxy, could develop even bigger signals visible over substantial fractions of the distance of the universe. So gravity waves have become cosmological tools, and that's really exciting. So that's a unification of quantum physics and general relativity, of course, and cosmology. The other one is always been true, which is that our best understanding of the quantum nature of matter may well come from study of the early universe. So given the difficulties of accelerators, given the difficulty of going much beyond what the Large Hadron Collider can generate, so we're up to sort of TeVs of energies in particle accelerators, it's really hard to imagine going much more than 10 times larger than that. The cost of that accelerator, the size of it, would just be phenomenal. So it's not that high energy physics is running out of steam, but that the scale of the experiments is just getting ruinously expensive. But the universe generated those energies, of course, effortlessly in the first tiny fractions of a second after the Big Bang. And so cosmologists are working the predictions of the Big Bang in this regime between when normal matter was created, the sort of baryogenesis, as it's called, which happened a microsecond after the Big Bang. In that regime, going back all the way to inflation, which is grand unification, and that's really physics we're not sure of. In that interval, there's the only diagnosis of all these quantum effects of this microscopic physics is the Big Bang. And so, physicists are not necessarily looking to the Big Bang to solve their problems, but the early study of the early universe, however we can do it, and typically that's going to be done by microwave background experiments, especially those that involve polarization measurement. We can diagnose gravity waves as well as the interactions of matter and radiation. Those are going to say some very important things about the fundamental microscopic world, which is exciting.
The next question is from Bruce Heyman via YouTube. What causes a white dwarf to explode when it exceeds the Chandrasekhar limit?
So white dwarfs on their own, an isolated white dwarf is just a stellar ember. It's a degenerate state of matter where the pressure that stops it collapsing further is a quantum pressure resulting from the inability or the unwillingness of two particles to share the same set of quantum properties. And so it's a stable stellar corpse of very high density. There's no energy generation, and so white dwarfs will just essentially cool forever. And the typical white dwarf, for example, that when the sun dies, it will lose 20 or 30% of its mass as a planetary nebula and then red giant. And the white dwarf that remains will be about 60 to 70% of the mass of the sun. And most white dwarfs in the universe are something like that mass or a bit bigger. But if the white dwarf is in a binary system, then you have the possibility after the star is dead and is a white dwarf, where really in general nothing else is going to happen, you have the possibility of reanimating the white dwarf. And that can happen in several interesting ways. In one way, if the massive star, let's suppose a massive star that has a big stellar envelope and can transfer mass across to its close companion, these have to be closely orbiting stars with orbital periods between them of hours to days, not weeks to years. If the mass transfers, then one thing that can happen is as the gas falls onto the surface of the white dwarf, it can be compressed by the intense gravity so quickly that it generates rapid fusion, and it'll do so episodically, because as the gas accretes and then reaches a flash of fusion, it will blow some of that gas off, will generate energy and brightness, and that will repeat. And that process, that's a nova. That's what a nova is essentially. So you can have a sort of episodic reanimation of the white dwarf by the addition of material that gets shock compressed by the gravity, ignites with fusion, blows off some material, brightens, and then the process repeats on a semi-periodic timescale of centuries to millennia. Or you could have enough mass transfer, maybe in a slow mode that doesn't lead to a nova, that you gradually you add enough mass to the white dwarf to put it above the Chandrasekhar limit, 3.5 solar masses. And if you did that, it would be a black hole. So the course of evolution of a white dwarf that's on its own is just set. There's nothing that can happen. It'll just slowly fade to black over the history of the universe forever. But a white dwarf that formed in a binary system with mass transfer can have some much more interesting eventual outcomes.
This next one is from Steve Koski via email. What was the size of the universe when the cosmic microwave background radiation occurred in relation to the present state?
Oh, and I should say, hi, Steve. I've known Steve a long time. Thanks for your questions. So the microwave background radiation, which we see now as, centimeter wave radio waves or microwaves, slightly smaller than centimeters, represents the universe when matter become neutral. So when the universe went from being a hot ionized gas or plasma of hydrogen and helium to being a stable neutral gas of hydrogen and helium, the coupling, and it's also called decoupling, because as the gas becomes neutral from having been ionized, the free electrons were the things that were scattering the radiation before that time, which meant the universe was in a fog and opaque. Those electrons suddenly being bound to the protons, or pairs of them to the helium nuclei, suddenly means the electron scattering of the radiation isn't happening, and so the radiation can travel freely. And so those sort of related events of decoupling and recombination lead to this surface, this edge of vision, which corresponds to the microwave background radiation. So when we look at the microwave sky and we see these ripples, we are essentially looking at that era when that event happened, straight back, because subsequent to that, those waves have been able to travel freely through space in straight lines, and so we see an image of the universe as it was then. So when was that? Well, the physics is fairly simple, because it's just the temperature at which hydrogen and helium become neutral. And that temperature is, of order 3000 Kelvin. The microwaves now are 2.7 Kelvin. So the universe was 1,000 times hotter when that was going on, or when that radiation was released, than it is now. And since redshift is directly related to temperature, because it's just those photons being stretched by cosmic expansion, that means the universe was 1,000 times smaller than it is now. So that radiation was released when the universe was 1,000 times hotter and 1,000 times, in round numbers, 1,000 times smaller than it is now, which means it was, of course, 1,000 cubes, so 1 billion times denser, which is pretty interesting. And then if you do the calculation in the cosmology for what time that was ago, because it's a nonlinear expansion, it's not as simple as saying it's 0.1% of the age of the universe, because that would give the wrong number. That would give you, that's a 13.8 billion-year-old universe, that would give you 1.3 million years. If you do the math, because of the nonlinear expansion, it turns out to be 400,000 years. So that radiation is coming from actually 380,000 years after the Big Bang.
Next question is from Richard Aguirre via YouTube. Are there any experiments being planned right now to detect gravitons?
There are, and have been actually for decades. So graviton it's part of the edifice of what's called the standard model of particle physics. And in the standard model of particle physics, there are 4 fundamental forces, and each of the fundamental forces has exchange particles, and those are the particles that carry that force, usually at light speed. For the electromagnetic force, of course, that particle is the photon, which we can think of as a wave or as a particle. For the weak nuclear force, those particles are bosons, those integer spin particles. The the W and the Z particles, 3 varieties of those 2 particles. And for the strong force, those particles are, of course, the quarks, of which we know there are six varieties. So those are all known and demonstrated to be the particles that carry the 3 forces of nature that are the stronger ones. The weakest force in this view should have its own exchange particle. And so it was hypothesized decades ago that gravity should have an exchange particle, which is called the graviton. And by sort of inference from the properties of gravity, the graviton should travel at the speed of light. In the quantum formulation, it has a spin of 2. It's just how it works out in the quantum theory. And the question is, can we show gravity propagating at light speed with transmission by a particle? And the simple answer is that no, and there's no physics experiment where that has been demonstrated. And most of the physics experiments are actually trying to do something simpler. It's not simpler once you try and work out how to do it, which is to show that gravity does propagate at the speed of light. Remember, to Newton, gravity just instantaneously manifested across the vacuum of space. There was no particle, there was no time lag, there was no speed of light, nothing. But if you think about the difficulty of switching gravity on and off, you can switch a light beam on and off and then watch the photons arrive, and that's a trivial experiment in modern physics lab. But switching gravity on and off and watching gravity arrive, if you like, at a remote location is not really something that we know how to do. So you, of course, end up doing something more subtle. You actually have to rearrange a microscopic object, which means you have to do it with particles, subatomic matter. If you change the configuration of the matter as close as you can to instantaneously and then look at the gravitational effect, then you might be able to see gravity propagating at the speed of light and infer that a particle did it. But remember, gravity is 10 to the 30-ish, forget the exact number of orders of magnitude, weaker than all the other forces of nature that are going on in your physics experiment. So it's extremely difficult to do this test of gravity as a particle in the physics lab. And in the universe, it's the worst problem because you just don't know how, we don't know how to switch gravity on and off in the universe and watch it propagate. So the simple answer is nobody's ever managed to demonstrate that the graviton exists as a subatomic particle and travels at the speed of light.
This next question, our final question of the day, is from Unair Wakar via email. I want to know exactly how dark energy is contributing to the expansion of the universe. Didn't the explosion at the time of the Big Bang contribute to the expansion?
Yes, it's a good question. So there is indeed kinetic energy, if you want to think of it that way, in classical physics terms, associated with the initial expansion. So dark energy is apparently, we really don't understand it in a fundamental sense, dark energy is a property of space-time. It appears out of the vacuum of space, and it appears with an equal strength as space-time expands, and that's actually what leads it to have negative pressure and leads to the accelerating expansion. Because even as there's more space-time created by expansion, the impetus of dark energy continues, which leads to an accelerating expansion. But if you go back to the initial conditions, to the Big Bang as it happened or just after it happened, then dark energy is essentially not a player at all. You have if you calculate the energy of the universe, the potential energy of all that gravitational material, all the stuff that's going to turn into 100 billion galaxies, or the kinetic energy associated with all that matter in very rapid outward motion early in the universe, those amounts of energy far exceed the contribution of dark energy, which has not changed over cosmic time and has not varied in a unit chunk of space as the universe has got larger and larger. So dark energy was simply not a player or not a contributor or not a factor in any of the energy calculations early in the universe. It took the universe growing and being diluted by a large volume for dark energy to matter. So basically, as the universe expanded, the contribution of energy declines faster than the contribution of gravity from matter. And that's because the photons are thinning out according to the volume, that's r cubed, but also the photons are stretching to the expansion of space-time, and that's the redshift. And so that's an extra factor. So the energy density of radiation goes down as r to the 4th, where r is the size of the universe at any time. the density of matter goes down as r cubed, just as the volume. So radiation becomes less important than matter after 10,000 years. And then from 10,000 years forward, you're talking about the gravity of dark matter mostly, and the smaller fraction of baryonic matter. And then dark energy is present in the universe when it's this size and dominated by matter, but it's not dominating the expansion. That transition happens about 5 billion years ago, when the dark matter has thinned out, so the gravitational effect of the dark matter in the ever larger universe is finally reduced to the point where the accelerating expansion impulse of dark energy matches it. And so for the last 5 billion years, as the dark matter thins out even more, dark energy has been dominant. And so we see the universe transition from a deceleration mode up until about 5 billion years ago to acceleration mode in the last 5 billion years. And that's an interesting situation because it implies a fair degree of coincidence in the energy density of dark matter and dark energy, that they would be so similar that they would be identical 5 billion years ago, and even now only a factor of 2 different. To some cosmologists, that's a coincidence that needs some explanation. So thanks very much for all your questions. Great variety today, as usual, and we'll be back in a couple of weeks. Thank you.